Hello. So this is a continuation of the lecture, a summary lecture on the MVT. Okay. So we want to continue from here and look at the consequences of the MVT. So there are three of them that we want to look at. Basically, these consequences are basically what we can use the MVT to do, right? We can use it to prove some other theorems. That is the consequences. But we can use it to show that if a function is constant and its derivative is zero. We can also use it to show that if two functions have the same derivative, then they differ by a constant. The difference between them is a constant, okay? And then we can also use it to show intervals where a function is increasing or decreasing, okay? I'm not going to prove these theorems. I'll basically put them up, and then we'll use them to solve some problems, okay? And then we'll move on to some applications. Okay, so the first one we want to look at is functions with zero derivatives. So this theorem says that if f prime, all right, if f prime of x is zero for all x in an interval, say AB, then the function f is constant on that interval, okay? And we can actually use MVT to prove this. I have the proof in my lecture notes, so you can look at the proof there, okay? The other theorem is that if two functions, f prime, if the derivative of two functions are equal, right? So if f prime of x is equal to g prime of x for all x in the interval AB, then f and g differ by a constant on the interval. That is, there is some constant c such that f of x is equal to g of x plus c for all x in the interval, okay? So if two functions are equal, it doesn't mean, if the derivative of two functions are equal, it doesn't mean that those two functions are necessarily equal. What it means is that one of them is the other function plus a constant, right? Or if you like, the difference between the two functions is a constant. Of course, that constant could be zero. In that case, the functions would just be equal. But this is general, okay? So that is what this is. And we can also use MVT to prove this. It's quite straightforward. And I have the proof again in my notes, which you can look at. So that is another consequence of the MVT, because we can use the MVT to prove it, okay? And then finally, we want to look at increasing and decreasing functions on an interval. I think you've come across this before in calculus 1, but this says that a function f is called increasing on an interval I if f at x1 is less than f at x2 whenever x1 is less than x2 in the interval, right? So if you look at this function is increasing here between x1 and x2. If that is the case, then I expect the value of the function at this point, right? Or if you like, at this point, which is f at x1, this value here has to be less than the value here. That's what it says. And if the function is decreasing, as in B here, if it's decreasing, then the value of the function at this point, that is this guy here, has to be greater than the value of the function at this. That is also here, okay? And we are saying this because MVT can help you to actually prove the theorem that governs this. And here's the theorem. The theorem says that if f prime of x is greater than 0 on an interval, if the derivative of the function is greater than 0 on some interval, then the function is increasing on that interval, right? And if the derivative is negative on an interval, then the function is actually decreasing on that interval. Okay, so here's an illustration of that. I have a function that is this black curve here, this sinusoidal curve. And this part of the interval, right? It is increasing, right? It increases all the way to the max here. So on this part of that interval, I expect f prime to be positive. Okay, that's what this says. On the other hand, if I know that f prime is positive, then I can just conclude straight away that the function is increasing on that interval. So, okay. And then here, the function is decreasing. It goes to the max and it's decreasing. Because it's decreasing here, the derivative of the function in this interval, this part of the graph, has to be negative. Also, on the other hand, if f prime is negative, then the function is decreasing there. And it's similar for this as well. Okay. So these are some consequences of MVT, because we can actually use MVT to prove this. And again, I have the proof of these this theorem in my lecture notes that you can take a look at. Okay. So here I just want to go on to some of the applications and how you actually solve problems using this. Okay. This is actually some notes you can read. You can look at this on how you find intervals of increase and decrease. You've done this before in calculus 1. All right. So you can look at that. How you find, given a function, how do you find the interval of increase and decrease? This is the procedure for doing that. So this is just a recap. Okay. The first thing is you find values of x for which f prime is 0, or where f prime does not exist. That is the critical values, right? You first look for the critical values. Then use the critical values to partition the interval into different intervals. Okay, like 3 intervals or something. Then in each of the sub intervals, right? In each of the sub intervals, you do this. Okay, you select some test value, right? And see whether f prime is positive or negative in that interval. If f prime is positive, then we know that the function is increasing on that interval. If it's negative, then the function is decreasing. If it's equal to 0, then f is constant on that interval, right? That is what we just showed. That's the first theorem on the consequences, right? If expansion is constant, then expect f prime to be equal to 0. Okay, so use this approach to just refresh your memory on how you do that using this. Okay, so I'm skipping this because this is not actually the focus of what we're doing now. So you can take a look at it on your own. Good. Then we want to end with applications of the MVT. The application basically has to do with how you use the MVT to establish an inequality. So often you are given an inequality, and you want to prove that inequality using MVT or some of the consequences of MVT, like increasing and decreasing functions, to establish, right? To establish the inequality. So I will do that using one of these examples, right? This says use the mean value theorem to prove the following inequalities. We want to prove that the cosine of x is greater or equal to 1 minus x for x greater or equal to 0. You can also use it to show that tan x is greater than x for x lying in the interval 0 to pi over 2. These intervals are important. This one, for instance, is important because tan of x, right, is continuous and differentiable between 0 and pi over 2, right? Beyond that is discontinuous, right? At pi over 2 is going to infinity. Tan goes to infinity. So that is why you have this, this restriction here. All right, good. So I'm going to look at, there are 3 ways you could do it. There are basically 2 methods. One of them is, of course, just using the MVT, which is the first one we'll do. A second one is very similar to this, so basically it's not any different. A third one is separate. You are not using the MVT formula directly. You are going to use the fact that the function is increasing or decreasing to prove the inequality. Okay, good. So in the first case, you are given this inequality here, and you are told that x is greater or equal to 0. So what you can do is that you can pick one of the functions in the inequality. In this case, it's easier if you use cosine of x. So we let f of x be equal to cosine of x for x in the interval 0 to some x. Okay, so this is a function we choose ourselves, and we are choosing this interval based on the information we have. We are going to start from 0 to some variable x, some x, right? For x positive. Good. Now we have chosen our function. We want to choose it such that it is continuous and differentiable, so that it satisfies the conditions of the MVT, the hypothesis, right? So, and we know the cosine is continuous and differentiable, so that's good. So by MVT, there has to be some c in this line in this interval between 0 and x. such that f prime of c is equal to that, right? Good. Now, in this case, our interval is 0 to x. So the b here will be x and the a here is 0. So you plug them in here in the formula. We also need to find the derivative of our function f at c. Now, we know f prime at x is negative sine x, right? The derivative of cosine is negative. So I can put in c, so f prime at c is negative sine c. Good. So I know the left-hand side, which is negative sine c. The right-hand side will just be f of x minus f at 0 all over x minus 0, right? It's equal to this side, which is negative sine c. F of x is the function, cosine of x. Cos of 0 is 1. So f at 0 is 1 here, all over x is equal to this. Good. So we are here. Now, from here, then you have to apply your knowledge, right? Your knowledge of some inequalities concerning trig. It could be trig, it could be rational functions, it could be roots, it could be whatever. But when you get here, you apply some previous knowledge on the function that you have here, and then try to get an inequality out of it. That is the point. Okay. Now we know that the sine is less than or equal to 1, right? Sine is bounded between -1 and 1. Therefore, we know sine has to be less than 1. So we use that knowledge. Sine c has to be less than or equal to 1. If I negate it, then I have to reverse this inequality sign here. So minus sine c has to be greater or equal to -1, right? If I negate both sides. Good. So we are doing this because the right-hand side here is negative sine. Now we know that the right-hand side is greater or equal to -1. Therefore, this expression here has to be greater or equal to -1, right? If you like, this is greater or equal to -1. Therefore, this has to be good. Now, because x here is positive, if you go back to the interval 0 to x is positive, you can multiply through by x, and the inequality here remains the same. Okay, so multiply through by x, and you have cosine of x minus 1 has to be greater or equal to -x. You can take the 1 to that side, and you have cosine of x is greater or equal to 1 minus x. Okay, and that is the inequality we wanted to prove. Okay, great. So basically, that is the procedure for doing it. Good. Okay, so I'll come back to a comment later on. But you could also have done it instead of choosing your function to be cosine of x. You could have chosen it to be cosine of x plus cos x plus x. Go back here. This is the inequality, right? So you can take x to this side, and that gives you cosine of x plus x. So you could have said that let my function f be cos x plus x, and you follow the same procedure. F is continuous and differentiable. Therefore, there is a c in the interval, and then you have all of this. Okay. Now your f of x is this guy. F of 0 is 1. So that is why you have this all over x. And now if you find the derivative, you're going to have negative sine x plus 1. So f prime at c is negative c plus 1. And so you equate the two, this and that, and you get this, right? And use the same idea of sine is less than 1, right? Sine c is less than or equal to 1 implies that negative sine c is greater than or equal to -1. You can add 1 to both sides. So you have negative c plus 1 is greater or equal to -1 plus 1 is 0. So you get 0 here. Okay. Or if you like, take this to that side, you get that. Okay. So this says that this expression here is greater or equal to 0. That means this is greater or equal to 0. Therefore, this has to be greater or equal to 0. So this is greater or equal to 0. Again, you can multiply through by x, and you have cos x plus x minus 1 is greater or equal to 0. Then you can take these expressions to this side, and that gives you cos x is greater or equal to 1 minus x, as we wanted to derive. So this method 2 is basically very similar to method 1. You just choose different functions, okay? And that is how you prove it. Now, the last one is a bit different in the sense that you are not directly applying the formula here in this case, okay? Sometimes you are just asked to prove, you are just asked to prove the inequality or establish it, and you are not told to use the MVT directly, right? So you could use the MVT or use the fact that a function is increasing or decreasing. And that is what method 3 is about. So in this case, you take you look at the inequality, it is here. All you do is that you can take all these expressions here to the left-hand side and then call everything there some function. Okay, that is the approach. You can take cos to that side as well. It doesn't really matter. So if you do that, then you can let f of x be equal to cos x plus x minus 1. Again, we choose our interval to be 0 to x. We want to show that f of x is greater or equal to 0 on this interval. If we are able to show this, then of course, then we can show the inequality, because then we'll just pick these guys to that side and then we get the inequality. So once we have this function, you want to be able to establish this. And once you establish this, then you have established the inequality. Okay, good. How do we show that this function is positive? That's basically the question. You can use the derivative of the function, right? So find the derivative of this. F prime of x will be equal to negative sine x plus 1, right? Or if you like, 1 minus sine of x. That is the derivative of this. Now, once again, we use our knowledge of sine to show that, to write that sine x is less than or equal to 1, right? Has to be. If you negate both sides, then you have negative sine x has to be greater or equal to negative 1. If I take the negative 1 to that side and I get 1 minus sine of x has to be greater or equal to 0. So I have established that 1 minus sine of x is greater or equal to 0. So this guy is greater or equal to 0, which means that f prime of x is greater or equal to 0. Okay, what does that mean? We just showed increasing and decreasing functions. There's a theorem that says that if the derivative of the function is greater than 0, is positive, right? Then the function is increasing on the interval. So this shows that the function f of x is increasing from 0 to x, okay, on this interval. If it's increasing, then the value of the function at this point, x, has to be greater than the value of the function at 0. Okay, we showed that using those graphs, those curves, right? So if it's increasing on this, then f of x has to be greater than f of 0. But we know the function f, so we can actually calculate f at 0. F at 0 is equal to cosine of 0, which is 1, plus 0 minus 1, so we get 0. So this guy is actually 0. So f of x has to be greater or equal to 0, right? So we have established what we wanted to establish. You see that? So since f of x is greater or equal to 0, then this thing here, this expression here is greater or equal to 0, which you have here. So you can collect these guys, take them to that side of the inequality, and you have cosine of x has to be greater or equal to 1 minus y, x. And that is another way that you can prove the inequality. Okay, good. There are instances where you have, let me probably write it here. Try to write it here, and then I'll show you what I mean. So there are instances where you are given the inequality, and the inequality is actually contains, let's say, 3 terms, right? You still can follow the same approach. Okay, if you have some expression here, function here, okay, you say it's less than or equal to some other expression, less than or equal to some other expression here. You want to establish this inequality. Well, one of the ways you can actually do that is you try to establish. One of the ways I'm saying is that you could try to establish one side of the inequality. Say, show that g is actually less than or equal to f. Okay. And then after you are done that, you can also show the other side, or prove that f is less than or equal to h, where h is some other expression. Then once you have these two inequalities, right, you can combine them, and then you have this. Okay. So in some of the problems, you have expressions that look like that, and you can still use MVT or increasing and decreasing functions to prove it. Other times you can use the interval that is given to you, right? And then when you manipulate that, this expression, this inequality here, these 3 terms will just come out. Okay. So sometimes that is what happens. So you could have cases like this, not just a single inequality. Okay, good. So let's go back to our full screen mode. I have to close this, and then I will show you some exercises and that you should try. Okay, so you should try to do this, guys. Use the mean value theorem to prove the following inequalities. Okay, in one of the videos, this was done for you. Okay, you could try this one too. And then this one says use the MVT to prove the inequality. Sine of A minus sine of B, absolute value of that is less than or equal to the absolute value of A minus B for all A and B are real, I think. Okay. Show that, this is another one, show that the square root of 1 plus x is less than 1 plus half x, right? If x is positive. So here you are not told to use MVT. You could try to use MVT or use the fact that the function is increasing or decreasing. So you can take this to this side and call everything there f of x and try to use the method 3 that we use. Find the derivative and try to show that the resultant expression is, let's say, less than 0, and then try to prove the inequality. Okay, good. I might do another video where I just solve some problems from your tutorial questions. I said, do another one. If I do, I will post it on Sakai or on my YouTube channel. Okay. All right. So all the best. Try your hands on these problems. This is the last one on this MVT. Okay. All right. My next video will probably be on inverse functions. So watch out for that that one too. All right.